Welcome to the video on the chemical potentials of liquids. So in order to discuss the mixing of liquids, we need to know how the Gibbs energy of a liquid is going to change with composition. So we're going to use the fact that at equilibrium, the chemical potential of a gas is equal to the chemical potential of the same substance as a liquid. So if we have, say, gaseous water and liquid water at equilibrium, at standard pressure of 1 atmosphere, that means we have to be at the boiling point of 100 degrees C for water. So at that point, the chemical potential of the gas is equal to the chemical potential of the liquid under the same conditions. So this only is the case if we're at equilibrium. If we're at, say, 97 degrees C, standard pressure, we're not at equilibrium. We may be continuing to condense gas, but we're not at equilibrium. So we've got a change that is spontaneously occurring. All right, so in our discussion, we're going to denote quantities of pure substances with a superscript star. Right, so note that on the last slide, where we said mu A star of gas, so this is the chemical potential of substance A when it's pure in the gas phase is equal to the chemical potential of substance A when it's pure in the liquid phase. So that star means it's a pure substance, and when we need to emphasize the state, we're going to include the letter designating the state in parentheses. So just like on the last slide, the L or the G was for liquid or gas phase. And so this is for substance A again. So over here, we've got sort of a generic container. We have some mixture of A and B in the liquid phase. We've got some mixture of A and B in the gas phase. And we have the chemical potential of A in the liquid phase. Note that here, because A is no longer pure, we're assuming that we have some amount of B present, we're writing the chemical potential of A no longer with the superscript star, because it's not pure anymore. A is not pure. And we also have a chemical potential of A in the gas phase at some pressure P. Now, if this is in equilibrium, if our container is at equilibrium and we're no longer, if we have no net vaporization or condensation of the gas, then the chemical potential of the gas phase is equal to the chemical potential of the liquid phase. All right, so the vapor pressure above a pure liquid, is PA star. So this is the vapor pressure of pure A, or the vapor pressure of A while it's pure. So this is star, and that means that then we can say that the chemical potential of A when it's pure in the gas phase is the chemical potential of A at standard conditions, still pure, plus RT times the natural log of the vapor pressure of A at those conditions while it's pure. So this is at some other temperature than the standard temperature there, divided by P naught. And so note that the P naught is 1 bar again. So this quantity, the mu A naught, is the standard chemical potential of our gas. So that's at standard temperature and pressure. So that means that now we can write this. So we know that the chemical potential of the gas is equal to the chemical potential of the liquid. So now we just don't change the right side, but leave that exactly the same. And now we can change chemical potential of our gas to chemical potential of our liquid. So if we have another substance that's a solute in our substance A, so if A is the solvent and B is our solute, then we can say that the chemical potential of A is mu A, and the vapor pressure of A is PA. And so now we're no longer working with pure A. So now we can say that the chemical potential of A, no longer including the star, in the liquid phase is equal to the chemical potential of A at standard conditions plus R times T times the natural log of our vapor pressure of A in this mixture, so while it's being a solvent, divided by P naught, or standard pressure. And now we can combine the two equations to eliminate our standard chemical potentials of the gas. So we get the chemical potential of the liquid in the mixture is equal to the chemical potential of the liquid in the in pure form minus RT times natural log of PA star over P naught plus RT times natural log of PA over P naught. And so now we can combine together these two logarithm terms, natural log terms, and so we get the chemical potential of our liquid for substance A is equal to the chemical potential of A while it's pure, still in the liquid phase, plus R times T times the natural log of the vapor pressure of A in the mixture divided by the vapor pressure of A while it's pure. So remember that the vapor pressure in a mixture is always going to be less than the vapor pressure of the pure substance at some temperature. And so French chemist Francois Raoult found that the ratio of partial pressure of each component of a mixture to its vapor pressure as a pure liquid is approximately equal to its mole fraction. So this is what we call Raoult's law. So the vapor pressure of the mixture is equal to the vapor pressure of that substance, the vapor pressure of A in a mixture is equal to the vapor pressure of A while it's pure times the mole fraction of A in that mixture. So if A is pure, if we have pure A, then the vapor pressure of our mixture of A and nothing is equal to 1, because the mole fraction of a pure substance is 1, times the vapor pressure. So that means that PA is equal to PA star. But if we have, say, half A and half B, now the vapor pressure of A will be half the value of the vapor pressure of pure A. This is half A, half B by number of moles. So mixtures that obey Raoult's law are called ideal solutions, and a mixture is likely to be an ideal solution if its components are very structurally similar. So if we have something like ethanol and methanol, let's say. Those are fairly similar structurally, but if we have something like water and a long hydrocarbon chain, those are fairly dissimilar structurally, and so we're likely to have a non-ideal solution. So here we have, again, Raoult's law, and what this means is that as we vary the mole fraction of A from 0 to 1, we will change the partial pressure of A from 0 to linearly from 0 to its vapor pressure while it's pure. Likewise, as we're increasing the mole fraction of A, we're decreasing the mole fraction of B. So the partial pressure of B at a mole fraction of A of 1 means the mole fraction of B of 0. So we go from 0 there, increase it linearly to the vapor pressure of component B while it's pure here at mole fraction of A of 1 of 0, mole fraction A of 0, and mole fraction B of 1. So this is pure B, and that's pure A. And what this means is that if we have a mixture, then the total pressure, so this is the sum of the blue and the purple lines, that gives us the black line. So if the vapor pressure of A while it's pure is less than the vapor pressure of B, then the slope here would be negative. If A has a higher vapor pressure than B does, then the slope would be positive. So this means that the chemical potential of our component, of some component in an ideal solution, is listed here. So we have the chemical potential of component A in liquid phase is equal to the chemical potential of A while it's pure, in its pure liquid phase, plus R times T times the natural log of the mole fraction of A. So note that here, to get this chi A, we've used this ratio. Right? If we solve this for chi, we get chi A is equal to PA over PA star. Well, this fraction, PA over PA star, that's what we have here. So we're just replacing this with our mole fraction chi to get this equation. So now we can use this equation as our definition of an ideal solution, because it doesn't assume that the vapor is an ideal gas, as this equation does. So Raoult's law assumes that our vapor is an ideal gas. This equation here doesn't have to assume that anymore, because now we're eliminating these pressures, and so we're just putting in the mole fraction. So some solutions can differ significantly from Raoult's law. So if we look at, for example, a solution of carbon disulfide and an acetone, so we get a plot that looks something like this. We expect as we change the mole fraction of carbon disulfide, we expect the vapor pressures to change linearly. So the dotted line here and the dotted line there. Know that this is the dotted line that we expect for acetone, and here's the dotted line we expect for carbon disulfide. With a total pressure, we expect to be linear between this point and that point. But that's not what we see. We in fact see this big curve there, and that's because the carbon disulfide is much higher at low mole fraction, or at rather high mole fraction of carbon disulfide. And the acetone has a significant deviation there at high mole fractions of carbon disulfide. All right, so note that as the mole fraction of the solvent then approaches 1, the deviation from Raoult's law decreases. Right? So as the carbon disulfide has a mole fraction closer to 1 as the carbon disulfide, which at greater than mole fraction of 0.5, carbon disulfide is the solvent. At mole fractions less than 0.5, the acetone is the solvent. So when the carbon disulfide is the solvent, the deviation from the ideal dotted line is smaller. And likewise with the acetone, when the acetone is a solute, the deviation is fairly large. When the acetone is a solvent, the deviation is fairly small. The deviation for acetone is fairly small. Alright, so in an ideal solution, the solute, in addition to the solvent, is obeying Raoult's law. But in real solutions, which we call ideal dilute solutions, sometimes they obey a different law, which we're getting to Henry's law. So, English chemist William Henry was the first to find that for real solutions at low concentrations, so ideal dilute solutions, vapor pressure is proportional to the mole fraction, but the proportionality constant that we use is not the vapor pressure of the pure substance as it would be for Raoult's law. So basically, has a similar form as Raoult's law does. The vapor pressure of component B is equal to the mole fraction of B times, in Raoult's law, this would be the vapor pressure of B while it was pure at that same temperature. But here we have some constant, Kb. And here that constant is not exactly the same, at least, as the vapor pressure of pure B. So this is an experiment, an empirical constant with units of pressure. So it's simulating the vapor pressure, but it's a different number. We pick the value here from experiments. So we plot the vapor pressure of B, that's this PB, against the mole fraction, chi B, and what the slope is, or the tangent to our experimental curve at a mole fraction of 0, so at mu dilute solution. That's what we're putting in here for Kb. So this equation then is what we call Henry's law. Again, it has a similar form to Raoult's law, but we're replacing it. It works better at dilute concentrations of B. So mixtures for which the solute obeys Henry's law, and the solvent obeys Raoult's law, we call ideal dilute solutions. So it's ideal because the solvent is obeying Raoult's law. It's dilute because the solute is obeying Henry's law. So it's an ideal dilute solution. So the reason for this is that the solvent molecules are in an environment very similar to the environment that they're in while in a pure liquid. So if we look over here, we've got some blue molecules. That's what most of these are. Those molecules are in an environment that are very, very similar to the environment they would be in while they were pure. So if it was pure, then these two red molecules would be blue. In which case, all the molecules in there would be in some environment. But when we replace those two solvent molecules with solute molecules, the solvent molecules, the environment looks almost the same for most of them. For a few of them, you've replaced a neighbor with that was a solvent molecule. You've now replaced it with a solute molecule of some different chemical species. But most of them, they're in about the same environment. But if we look at the solute molecules, so the red ones over here, those are in a very different environment from the environment that they are in while in pure solute. So if we look at these red molecules, the red molecules now are surrounded by blue molecules. Well, in their pure form, the red molecules would be surrounded by red molecules. So they're in a very different environment. So if the red molecules and the blue molecules are very similar, then the environment that the red molecules are in is very similar to the environment they would be in the pure form. And so this is why Raoult's law is followed more closely by two compounds that are, or two substances that are very similar structurally, because the environment will be the same, or very close to it. But if we have two things that are very different, if we have, say, oil and water, the oil molecules dissolved in water are in a very different environment than they were in while they were in the pure oil matrix. So this means that the solvent molecules are obeying nearly the same. They exhibit nearly the same properties as they would for the pure substance, which is why the solvent is acting ideally. The solvent is in basically the same environment, or almost the same, so it's going to obey Raoult's law. But the solute molecules are in a very different environment, so they're going to behave much differently than they would compared to their pure substance. So the solute molecules are going to be obeying not Raoult's law, but Henry's law. So often in practice, Henry's law is expressed in terms of the molality, so B of the solute. So we replace the mole fraction with the concentration in molality, so B. And now we're going to have a different than K here. So note here that Henry's law can also be used to calculate the solubility of a gas in a liquid, which can be important then in a discussion of respiration. So especially when partial pressure of oxygen is abnormal, like in scuba diving and mountain climbing. So if we go mountain climbing, the partial pressure of oxygen is much, much lower than it would normally be. If we go to elevated heights, the partial pressure of oxygen drops, the partial pressure of all gases are dropping, because the total pressure is dropping. So if we go to, say, the South Pole Station, you're 10,000 feet up, or thereabouts, and so you've lost about 20% of the atmosphere, which means instead of a partial pressure of around 0.2 atmospheres of oxygen, you have a partial pressure of around 0.16, maybe a little bit less. And so you've lost a good deal of the oxygen that is present there, and so that's going to have a big impact on the solubility of oxygen in the blood. And this is why, as humans, we have difficulty breathing at elevated heights. If you continue to go up, you will eventually pass out. On the other hand, if we go scuba diving, we don't need as much in terms of a fraction of oxygen in the air because the total pressure is higher. And so we only need around 0.2 atmospheres of air, of oxygen rather. And so, but in scuba diving, the total pressure is much higher. The total pressure of air in your lungs is much higher because you've got all this weight of water pressing down on you. The water exerts a pressure of about 1 atmosphere for every 33 feet you go down. So if you're 66 feet down, you have 3 atmospheres being exerted on your body, where at the surface you'd have 1 atmosphere from the air. If you go down 33 feet, you've got another atmosphere from the water. If you go down 66 feet, you've got 2 atmospheres from the water, and so on. And so if you go scuba diving, you very quickly build up pressure on your body, which means that now the air inside your lungs is at significantly higher pressures. And so now the partial pressure of something like nitrogen is much, much higher. So much, much more nitrogen gets dissolved in your blood, and which is fine as long as you stay at that pressure. But if you very quickly come up from 66 feet down and come back from 3 atmospheres to 1 atmosphere, you're now going to drastically change the solubility of nitrogen in your blood. When you do that, if you rapidly come up and that nitrogen doesn't have a chance to come out of your blood, if your blood is super saturated in nitrogen, then you start to form little bubbles of nitrogen in your blood, which is really, really painful, and it really hurts, and this is what we call the bends. And so, this sort of effect becomes really significant in certain real-world scenarios. So that was the chemical potentials of liquids.